Let us calculate the center of mass of a solid hemisphere. So we have a solid hemisphere of mass capital M and radius capital R. Now to consider, and this is symmetric about y-axis. So if it is symmetric about y-axis, center of mass, basically x coordinate and z coordinate are going to be 0, 0, right? So we just need to calculate YCM. And what is YCM? The formula is 1 by m integration y dm. So what is y? So first we will go here. So we are going at y height. Okay, so we are going at a particular y, then taking a section which is having a width dy, right? And now basically what will that form? So this is a solid hemisphere. If we cut it like this in slices, this is going to be a disc, right? So a disc at y height, and the thickness of the disc is basically dy. Now where the center of mass of this disc lie is somewhere over here, because it is the full disc and center of mass lie exactly in the middle. Now y is nothing but y, because we have went up to y height and center of mass lie there. So that is the position of the center of mass where this dm lies. And what is the dm? Dm is basically mass of that disc. How do you find mass? So total mass divided by total what? Volume, because the mass is distributed in a volume, right? So total mass of a volume. So what is the volume formula? 4 by 3 pi r cube is the volume of full, right? The complete solid sphere. So here it is going to be 2 by 3 pi r cube is equal to required mass, which is dm, divided by required volume. So how do you find the volume of this disc? So volume of this disc is going to be the area. So what is the radius? Here radius is, let's say, r. So area is going to be pi r square, area of this area, into width. What is the width? Width is like dy. So into width, so that is dy, and that is going to be our volume. To be precise, the small volume, I am calling it dv. Now what is this r? So if you relate over here, so this is r radius, this is y, and this is capital R. So I can apply Pythagoras theorem, and I can say that this y square plus r square is equal to capital R square. We need this r square. So this is going to be pi capital R square minus y square dy, right? So this is going to be our volume. And now this is what we need to put it over here. So pi r square minus y square dy. And now let us cancel whatever we can. So this gets cancelled and this goes here. So we get our dm equals to 3m r square minus y square dy divided by 2r cube. So this is the dm, this is my y. And now let us integrate y. Y varies from where to where? When y was 0, we were getting the base. And when y is r, we'll get the topmost layer, right? So y changes from 0 to all the way up to r. So let us do this integration. So this is 1 by m integration y. Dm was 3m r square minus y square dy divided by 2r cube. Let us take the constant outside. What were the limits? Limit was y was varying from 0 to r. And now take things outside. So m is cancelled. This is constant, will come out of the integration. This 2r cube is also a constant. This 3 is also a constant. And this y is going to be multiplied. So r square y minus y cube dy. This is what we need to integrate. So let us integrate 3 by 2r cube. Integration of this is going to be r square, which is a constant, y square by 2 minus y raised to 4 by 4. Put the limits 0 to r. Putting the limits, we get, first put r over here. So r raised to 4 by 2 minus r raised to 4 by 4. And when you put 0, you get basically 0. And now let us solve this. So this is basically half minus 1/4, so which will give you 3 by 2 r cube times r raised to 4 by 4. So cancel this r cube with power 4. We get 3r by 8. And that is going to be our y coordinate of center of mass. So we can say center of mass of a solid hemisphere lie at a height of 3r by 8. That is going to be our y coordinate of center of mass. What about x and z? X and z are 0 due to symmetry. So this is y coordinate of center of mass is 3r by 8. That is what you need to remember.